Here is the NMR spectrum of a compound which has the molecular formula C9H12. And since the molecular formula has already been given, the best place to start here would be to find the degree of unsaturation. The degree of unsaturation has a formula 2C plus 2 plus nitrogen minus halogen minus hydrogen divided by 2. So for this compound, let's find the degree of unsaturation, which is going to be 2 times of 9 plus 2. There are no nitrogens, therefore it's going to be 0. There are no halogens, it's going to be 0 again. And the number of hydrogens here is 12 divided by 2. So it's going to be 18 plus 2 minus 12 divided by 2. That's going to be equivalent to 8 divided by 2 equivalent to 4. So this compound has definitely got unsaturation in it. So which means there could be double bonds, triple bonds, or ring structures. For analyzing the NMR, I will always like to use this table, okay, which is going to help us to determine the compound more precisely. Okay, I'm going to go from the shielded region to the downfilled region and list down the different peaks with its chemical shift and the multiplicity, and also the neighboring protons that it has. Okay, so to begin with, let's take the very first peak in the upfield region. So this peak is starting around 0.9. So I'm going to write it as 0.9 ppm. Okay, and the total number of protons can be seen from the integration value here. So this equates to 3 protons, so 3 hydrogens. And the multiplicity right here is actually triplet. So if you blow up this spectrum, or the blown up spectrum has blown up part of the spectrum is given here. So you can see there are 3 peaks, and therefore it is a triplet, which gives us an idea that this proton should be adjacent to 2 neighboring protons. So the total number of neighboring protons this proton has is 2. Okay, so I know, or we all know that the CH3 protons is the one that's going to come around 0.9 ppm. So if I'm going to imagine the CH3 proton is adjacent to something which has 2 protons, it's going to look like this. Okay, so I'm going to highlight that this peak at 0.9 ppm is going to correspond to the CH3 protons, and which is adjacent to 2 neighboring protons. Let us now go on to the next peak on the left. So we have a peak around 1.6 ppm. So let's write it down, 1.6 ppm. And the total number of protons this peak accounts for is 2 hydrogens, which can be seen right here in the integration. Okay, so that's going to be equivalent to 2 hydrogens. Let's look at the splitting pattern for this. Here is the blown up spectrum, blown up part of the spectrum for this peak. So, and you can see there is 1, 2, 3, 4, 5, 6. The multiplicity is sexted, which means it definitely tells us that there are totally 5 neighboring protons. So what we can imagine is if a CH2 is in between, we already know that there is a CH2. Right? So if there is a CH2 in between a CH3 and a CH2, then that definitely accounts for 5 protons, right? So here is my CH2. Okay, and the next thing is, if we go on to the next peak, this peak starts around 2.6 ppm, and the total number of hydrogens for this peak is 2 hydrogens. Okay, let's write it down, 2 hydrogens, and it is split as a triplet again. So 1, 2, 3. So which also tells me that there are 2 hydrogens, 2 neighboring hydrogens. So triplet and 2 neighboring hydrogens. So we accounted for this CH3 and CH2. But for this CH2, if I could imagine that there are 2 neighboring hydrogens, then these are the peaks, these are the protons that's going to result in the triplet, right? So if I'm going to write it down, this peak at 2.6 ppm is going to correspond to these 2 hydrogens, which should be split as a triplet. Now the last peak that we have is in the aromatic region of the NMR spectrum, and here we see a multiplet around 7.2 ppm, right? 7.2 ppm, which is equating to about 5 hydrogens. And this definitely tells this pattern is going to be consistent for the monosubstituted benzene ring, which is going to look like this. Okay, so and we have these 5 hydrogens, and those 5 hydrogens are going to be appearing as a multiplet in the NMR spectrum. And we have already found this X because there are no other hydrogens present in this molecule, right? Other than the ones that is present in the propyl group and the ones that is in the aromatic ring. So we can easily conclude that this X is nothing but the propyl group that we found using the values for the different peaks. So on the whole, the identity of this compound, which has the molecular formula of C9H12, is nothing but propyl benzene.